Hi everyone, the topic for this video is acceleration. The average acceleration is defined as the rate of change of velocity. A average, it's a vector, is delta v divided by delta t. So it's v final minus v initial divided by t final minus t initial. As I just mentioned, acceleration is a vector quantity having magnitude and direction. You can see it's because we divide a vector by a scalar. We don't use relative acceleration rules. I'll say a little bit more about that later on. And instantaneous acceleration can be defined using calculus, but we will instead study it with graphical methods. That's what I closed out the last video with concerning instantaneous velocity. So instantaneous acceleration has the same issue. We need to use graphical methods instead of calculus. Most problems in an introductory physics course feature constant acceleration, and so instantaneous acceleration is rarely used. So we don't really need to worry about instantaneous acceleration. Instantaneous velocity is a little bit more useful even in this class. Let's talk about the definition of average acceleration. We just define average acceleration to be the change in velocity over a corresponding time interval. So A average is equal to delta v divided by delta t, and v final, that's v final minus v initial divided by t final minus t initial. Go ahead and compare that to the way that we defined the velocity as the change in displacement over time, over a change in time. I'll have more to say about that in a few minutes. The dimensions of acceleration are length per time squared. We have a length per time in the numerator, so let's be explicit about this. Velocity is a length divided by a time, and that's being divided by a time. Again, don't forget that just because don't forget that when these are subtracted, it doesn't change the units at all, or it doesn't change the dimensions at all. So we have length divided by time, and so we get length divided by time squared. The SI units are meters per second squared. Some textbooks and occasionally just some parts of textbooks, or maybe in some of my videos, we write that as meters per second. And some students, I think, find that a bit more intuitive, and they say, oh, it's the number of meters per second of velocity that are changing each second. So it's meters per second per second. I think that that's a little bit confusing. I just say use meters per second squared, or use whatever you're comfortable with. But I think that you should be comfortable with using meters per second squared. Like velocity and displacement, acceleration is a vector quantity with a magnitude and direction. I've said this a couple times now, but we had a vector quantity in the numerator and a scalar quantity in the denominator, and so when we divide a vector by a scalar, we get a vector. And in one-dimensional motion, non-zero acceleration is always associated with a change in speed. In two-dimensional motion, we will study a situation with constant speed but non-zero acceleration. So as long as we're working in one dimension, it's actually kind of nifty. Acceleration just always means that something is speeding up or slowing down. So that's really handy. But in two-dimensional motion, acceleration doesn't necessarily mean that something is speeding up or slowing down. I'd like you to try to hold on to that in your mind, because a lot of students get tripped up by that and think that acceleration means that the speed of an object must be changing. All right. But here's an example. Again, I like to lead with simple examples. A model rocket is launched from rest, and let me be clear about this. When we use the phrase from rest, and you'll see this throughout the course, from rest means v equals 0, the speed equals 0, initially at t equals 0. By convention, we usually take the initial time of the problem to be t equals 0, but the velocity, when you see that phrase from rest, it means that the velocity of the object in question is 0 initially. After 5 seconds, it is traveling at 15 meters per second, and after 12 seconds, it is traveling at negative 48 meters per second. So I'd like you to find its average acceleration over A, the first 5 seconds, B, over the last 5 seconds, and C, over the entire 12 seconds. this would be a good time to pause the video. You may want to go back to the previous video on average velocity and see how those were computed. We did a very similar problem there. I'll tell you that the steps are very similar here. And so this is a good time, if you weren't able to do that previous problem, to go back and review it and hopefully do this one without my guidance. But here we go. We'll define T0, the initial time, is 0 seconds, or 0. We don't need to write units on that. T1, the first time in question, is 5 seconds. And T2, the second time that we're interested in, is 12 seconds. V, I'll put a vector sign over it. V0, the initial velocity, started from rest, was 0. You could say meters per second, or I could leave the units off. V1 is equal to 15 meters per second. That does need units because it's a non-zero quantity. And V2 is equal to negative 48 meters per second. All right. This was a model rocket. I didn't specify whether it was launched vertically or horizontally or anything else, but let's take it to be launched vertically. And I've been a bit, I don't know, haphazard about including my my coordinates. I'll say that the positive y direction is upwards. We're not going to see y as a variable in this problem statement. It's just implied that all of these velocities are associated with motion in the y direction. And so this is all I need to draw to specify that upwards is positive. All right, part A was to find its average acceleration over the first 5 seconds. Well, A average was V final, which was V1, minus V initial, which is V0, divided by T1 minus T0. That's the first 5 seconds. It's from T0 equals 0 to T1 equals 5 seconds. Well, what's that? Let's do that calculation. That's 15 minus 0 divided by 5 minus 0. 15 divided by 5 is 3 meters per second, or meters per second squared. Don't write meters per second. You have to write meters per second squared. Those are the correct units. Part B, as for the average acceleration over the last 7 seconds. Or the last 7 seconds there. So, what's that? Average acceleration is the final velocity, v2, minus the initial velocity. These are just the last 7 seconds, and so our starting time is at the 5 second mark. So it's v2 minus v1 divided by the corresponding time interval, t2 minus t1. So I think yes, this is v2 minus v1 over here. Okay, but the point is that we get negative 48 minus positive 15 divided by 12 minus 5. All right, in the numerator, that's going to be 30. That's odd. What do I have here? Oh yeah, in the numerator I get negative 63, and in the denominator I get positive 7, and so negative 63 divided by 7 is negative 9 meters per second squared. All right, go ahead and verify that calculation if you haven't done so already. Part C. Average acceleration is, part C was find the average acceleration over the entire 12 seconds, and so our time interval ends at, our time interval ends at our final velocity, and it begins with our initial velocity, and we divide that by t2 minus t0. Again, always note that the subscripts correspond. So v2 and t2 here, v0 and t0 here. v2 minus v0, t2 minus t0. and likewise for the other expressions that we found for parts A and B. All right. Well, what's that? That's negative 48. How fast was it going initially? 0. What was its time interval? Ended at 12 seconds, started at 0 seconds, and so it's negative 48 divided by 12, which is negative 4 meters per second squared. Again, verify that calculation on your own. All right, so that's it for that little problem. You should be able to do similar problems as well. When does it end? When does it all end? We began by introducing displacement, x. We denoted that as x with a vector sign over it. And then we defined the average velocity to be delta x divided by delta t, or x final minus x initial divided by t final minus t initial. I'll just briefly say this. In the previous problem, we had a y-axis here, but no x-axis. And so, yeah, you can have the average velocity in the y direction. That's y final minus y initial divided by t final minus t initial. Okay, but that's the point is that we found the average velocity as x final minus x initial divided by t final minus t initial. Now we've defined the average acceleration to be v final minus v initial divided by t final minus t initial. We just took the quantity that we found previously, the average velocity, and that sort of wormed its way into the numerator, and we defined this new term called the acceleration based on it. And we can take this even further if you want. You may be asking, gosh, are we just going to do this again? We can define the average jerk as a final minus a initial divided by t final minus t initial. This is an honest-to-goodness term in physics. Jerk is a change in acceleration. Don't bother writing this down. Don't bother writing it down because we're not going to use it. It's not necessary to memorize this equation because we'll never use it. So our study of kinematics, that's actually the topic that we're working on right now. Things involving position, velocity, and acceleration, or displacement, velocity, and acceleration. Those are all kinematics. Our study of kinematics is leading up to an intuitive understanding of acceleration so that we can apply and interpret the results of Newton's second law, F net equals mass times acceleration. So we need to have acceleration under our belts to do some real physics. This to me is the first real physics of this semester. All physical laws in the remainder of the course will be written only in terms of displacement, velocity, and acceleration, and there is no need to continue analyzing higher order rates of change. So you don't need to memorize jerk, you don't need to consider the change in acceleration over a change in time, and you don't need to consider a change in jerk over a change in time. Furthermore, the majority of problems in an introductory physics course result in constant acceleration, and so there's no need to analyze the rate of change of acceleration, because if the acceleration is constant, then the rate of change of the acceleration is 0. And so your jerk, if you're interested in it, is always going to be 0. So the question, I started with the question, when does it all end? And the answer is here. So if you think that that physics is just all about, going deeper and deeper down this hole and changing acceleration over time or changing jerk over time or something like that, don't think of it that way. It's displacement, velocity, acceleration, and we're done. That's things are just no longer interesting after that, at least to a physicist, for the most part. What about relative acceleration rules? We had relative displacement rules. I said that you could take the time rate of change of those and you get relative velocity rules. What if we just take the time rate of change of those? Could we get relative acceleration rules? So recall for relative displacement, here's our relative displacement rules. Should look very familiar to you by now. Correspondingly for velocity, here's our relative velocity rules. And so can we do the same for acceleration? Can we write acceleration of b relative to a equals negative acceleration of a relative to b? Acceleration of a relative to c is equal to acceleration of a relative to b plus acceleration of b relative to c. Technically, yes we can. Technically, nothing is preventing us from writing or using relative acceleration rules. They are mathematically valid. The deeper issue is that whereas all displacements and velocities are relative, there is a measurable zero acceleration. So, if you are flying in an airplane at a steady speed and in a straight path, you feel as if you're sitting perfectly still. You don't feel like you're moving at all. It works really well if you're on a very smoothly traveling airplane or along a flat, straight road that has some very nice, smooth pavement. So don't do that as a driver, but as a passenger, if you're ever in a car, close your eyes on a nice, flat, straight road with smooth pavement and think about whether you can feel yourself moving. You might feel vibrations in the car, but you shouldn't feel like there's a difference between moving at 60 miles an hour and sitting perfectly still. Okay, so according to the laws of physics, you are sitting perfectly still in your own reference frame, and there are no experiments that you can conduct that will convince you that you are moving. So like I said, you feel the vibrations of the car or the airplane, but it might just be that you're sitting still. You know, you might be sitting still in your bedroom and there's something vibrating in the floor, and that would produce a very similar sensation to you're feeling in the airplane or in the car. So if the plane speeds up or slows down, or turns, or experiences some turbulence, you will feel the acceleration. Think again about what each of those would feel like. So if it speeds up, what happens? You feel it pressing on your back. It has to accelerate you. If it slows down, then you kind of fly forward a little bit. You have to decelerate. If it turns, you begin to sway from side to side. If there's some turbulence, it's jostling you up and down. You will feel those accelerations. This means that accelerations are not relative, and it is a bad idea to apply the relative acceleration rules. Again, mathematically valid, physically not all that useful. When you get deep into physics, or if you get deep into physics, we actually do apply relative acceleration rules, but we have to interpret those very carefully because you end up throwing out a lot of good physics if you do that haphazardly. All right, let's talk briefly again about instantaneous acceleration, just as I did with instantaneous velocity. Just as we did with velocity, we can define the instantaneous acceleration as the average acceleration over a very short time interval. Again, if we are using the notation that we use in calculus, a, not a average, but just a, is equal to the limit as delta t approaches 0 of delta v divided by delta t. And over a very short time interval, both the numerator and the denominator should go to quantities very close to 0, but not be exactly 0. So this is the acceleration at a particular instant in time, and it's not associated with a time interval. As with the instantaneous velocity, we will not pursue a mathematical description of instantaneous acceleration because this is not a calculus-based course. Instead, we will find the instantaneous acceleration using graphical methods, which is the subject of the next video. Actually, we won't cover instantaneous acceleration in the next video, but we'll cover average acceleration, and then in the following video, we'll cover instantaneous acceleration. As I mentioned earlier, most introductory physics problems involve constant acceleration, and so there's no distinction between average and instantaneous acceleration. And so, yeah, we don't actually use the instantaneous acceleration all that much. I'd like you to be comfortable calculating it. It's not especially difficult, but in terms of, especially in an introductory course, are you going to see changing accelerations? Not all that much, no. So in summary, acceleration in one-dimensional motion is associated with speeding up or slowing down, and the average acceleration is defined as this quantity, a average, it's a vector, is delta v divided by delta t, which is v final minus v initial divided by t final minus t initial. And that's really the only new piece of information that you get from this video, because we don't use relative acceleration rules, and we're not going to take we're not going to be concerned with changing acceleration. So we'll analyze instantaneous acceleration with graphical methods. That's a topic for a video, a couple videos down the line. But in terms of mathematically, what can we do with acceleration? This is pretty much it. So commit that to memory, be prepared to use it, and I'll see you in the next video. Bye-bye.